Good morning. Good morning, students. Good morning. Today we are going to start a new module, direct and bending stresses. Okay, let me share the screen. Good morning, all. See, before starting this new module, I request all students, please recollect the topics which you have learned in your strength of materials 1. Why? Because in your strength of materials, if you remember, in the first unit, we have learned about simple stresses and strains. In the simple stresses and strains, all bodies are subjected to direct loads. What do you mean direct load? Direct load can also be called as a normal load or can also be called as a longitudinal load. Okay, so that means a load which is passing through the axis of the member, okay, or the load which is parallel to the longitudinal axis. If you take a beam, normal rectangular beam, if the load is passing through the longitudinal axis of the beam, so that load is a direct load. Direct load will always perpendicular to the cross section. Direct load will be always parallel to the longitudinal axis. Okay, so that is how you have learnt simple stress and strains like tensile stresses, compression stresses and all. Then how you calculate the direct stress? How you define a stress? Stress is defined as a resisting force towards an applied load at a given cross-sectional area. So that is what a direct stress. How you calculate the direct stress? Resisting force to the cross-sectional area, isn't it? So that is what a direct stress or a direct load. Coming to bending stress. Go back to your strength of materials again. In the second unit, there are topics called shear force and bending moment. Clear? So in shear force and bending moment, are the load is parallel to the longitudinal axis? No. There, the load is perpendicular to the longitudinal axis. Kada? In your shear force and bending moment, load is perpendicular to the longitudinal axis, right? So that's how your shear force and bending moments was calculated for a beam. Why? Because in practical, all beams will be subjected to lateral force. Dani direct force అనకూడదు, lateral force అనాలి, లేకపోతే vertical load అనాలి, okay, లేకపోతే bending load అనొచ్చు. Understand? So that is what about a bending. So due to lateral force, beams will undergo bend. Due to direct force, the same rectangular cross-sectional beam will undergo elongation or will undergo compression. Kada? So that is how individually we have studied direct stresses on a different cross-sectional members, bending stresses on a different cross-sectional members like beams. But in this strength of materials 2, what this unit is talking about, direct and bending stresses. Ante, is there any structural element which is subjected to both direct and bending stresses? Direct and bending stresses rendu act a structural element. Yes, we have. So that structural element is column. Guys, please mute yourself.
13 years 12 years पेल्ड करना
Okay, so the structural element which is subjected to both direct and bending stresses is a column. Why? Because column is a vertical member which is subjected to compression force. If you take a column will have an axial load. That axial load itself is a direct load. Okay. For example, if the load is not at center, what happens? If the load is with some eccentricity, obviously the column will have both direct and bending stresses. That is how in this unit we are going to study in detail about direct and bending stresses which is acting on column specially. Understand? So there is a cyclic manner. Why strength of materials 1 dealt with those topics, why strength of materials 2 is dealing with these kind of members అనేవి మనం అర్థం చేసుకోవాలి. Okay, so before going into subject, I would like to show you one video. Okay, so to understand better about what are the different types of stresses. Okay, Namma? Why? Because you all should have the visualization. Okay, that is my major motto. So because instead of just telling the statements, okay, just drawing the diagrams, it doesn't mean any sense. Okay, let me show you some video which gives a clear picture on, okay, how the stress is gonna act. What is direct stress, what is bending stress, what is shear stress. Okay, so these are all we will have a animated video. Okay, gonna present here. One second. Guys, అందరికి వీడియో కనిపిస్తుందా? Are you able to see the video? Guys, can I play it?
Yes, sir.
Yeah. So here we can able to understand the stresses in a beams. Okay, how the stresses acts in a beam. Based on that, what is bending stress, what is shear stress, that we will come to know. If you understand this, then you can able to understand easily how the direct and bending stresses both will act in the column. Okay, so that to understand that better, you have to go through this. Okay, please follow the video and don't talk in between. Any doubts you can ask last. Okay, at last of the video, right?
If we apply a load to a beam, it will deform by bending. This generates internal stresses, which can be represented by a shear force acting in the vertical direction and a bending moment. The shear force is the resultant of vertical shear stresses, which act parallel to the cross-section, and the bending moment is the resultant of normal stresses, called bending stresses, which act perpendicular to the cross-section. It's important to have a good understanding of these stresses because any design or analysis of a beam will involve calculating them. Let's look at bending stresses first. To keep things simple, we'll consider a case of pure bending. A section of a beam is said to be in a state of pure bending when the shear force along it is equal to 0, and so there is a constant bending moment along its length, like there is for this beam loaded by 2 moments. We also have a case of pure bending over the middle section of this beam, where the bending moment is constant. Let's look at how a beam deflects when it has a constant bending moment along its bending over the middle section of this beam, where the bending moment is constant.
Yeah, so this is very, very important, Amma. Here I would like to give a clarity on why this is pure bending. Why this example is pure bending?
Shear force becomes 0, sir.
Very good. See, pure bending means if you take any example in a beam which is subjected to point load, UDL load, or whatever it is, okay, so your shear force and bending moment diagrams should not coincide. Okay, and wherever the bending moment there, your shear force should not exist. Okay, so shear force 0 ఉన్న చోట bending moment ఉందనుకోండి, so that bending moment we are supposed to be called as a pure bending అన్నమాట. So that's the reason why we derived this pure bending equation for this example, where is simply supported beam subjected to 2 point loads at on the beam with some distances. Okay, so this is a pure bending. Why? Because your shear force is 0 at this particular point. Okay, at this particular distance. Okay, right, continue.
Let's look at how a beam deflects when it has a constant bending moment along its length. If we imagine the beam as a collection of very small fibers, as the beam deflects, the fibers at the top of the beam get shorter, meaning that they are in compression, and those at the bottom of the beam get longer, so they are in tension.
See, even you can relate this with the curved beams which we taught yesterday. Kada? Even curved beam also, at outmost layers it will be under tension and inmost layers it will be under compression. Okay, there also you can relate the same concept. Okay, in curved beams.
Somewhere between the top and the bottom of the cross section, there will be a surface containing fibers which stay the exact same length. This is called the neutral surface. It passes through the centroid of the cross section. When looking at the beam in 2 dimensions, we refer to it as the neutral axis. Let's try and quantify the bending stresses that develop within the beam to resist these applied moments. First, let's calculate the strains in the beam. This can be done quite easily just by considering the geometry of the deformation. Let's watch how a fiber at the neutral axis between points A and B and a fiber between points C and D located at a distance y from the neutral axis deform. Since this is a case of pure bending, we can see that the fibers bend into a perfectly circular arc. We'll call the center of the circle O. Before any deformation, the fibers are all the same length. After the deformation, the length of the neutral axis has stayed the same, but the length of the fiber between points C and D has increased. If theta is the angle of the arc and r is the radius of the arc to the neutral axis, we can calculate the length of the arc between A and B, like this, and we can calculate the length of the arc between C and D in the same way. Strain is defined as the change in length divided by the original length, and so we can derive an equation for bending strain at any distance y from the neutral axis.
I think you all learned this in your strength of materials 1 in deriving the pure bending equation, right? The
We
same
define the
he is
distance
also
y
explaining.
as being positive downwards, and so this equation will give us a positive strain for the bottom of the cross section, which is in tension. Sometimes you'll see this equation written with a minus sign, but that's because y was defined as being positive upwards. If we assume that stresses remain within the elastic region of the stress-strain curve, we can then apply Hooke's law for uniaxial stress to calculate the bending stresses. This gives us the equation for bending stress as a function of the radius of curvature, r, of the deformation. But what we're really interested in is how the bending moment, m, affects the bending stress. If we make an imaginary cut through the beam, we can expose the internal bending stresses, represented here as a few discrete forces. The resultant moment of these internal forces must be equal to the bending moment m, and so we can calculate m by integration, like this. Now we can plug in the equation for bending stress we just derived. When rearranged into this form, we can notice that the integral on the right is the definition of the area moment of inertia. This parameter, which I've covered in detail in a separate video, defines the resistance of a cross-section to bending due to its shape and is denoted using the letter I. We can combine this equation for the bending moment with the bending stress equation to obtain what is known as the flexure formula. So what does it tell us? Bending stress increases linearly as the bending moment and the distance from the neutral axis increase, and it decreases as the area moment of inertia increases. The maximum stress occurs at the fibers furthest from the neutral axis. The term I over Y max depends only on the geometry of the cross-section, and so it is called the section modulus, and is denoted using the letter S. you will often see the section modulus listed for a range of common beam cross-sections in reference texts. The I-beam is a commonly used cross-section because it has a large area moment of inertia, which results in lower stresses. Here's how the bending stresses are distributed over an I-beam cross-section. They are zero at the neutral axis and reach a maximum at the outside surfaces of the flanges. For a T-section, the neutral axis is shifted upwards, and so the bending stress distribution looks like this. So we've established how to calculate the bending stresses, which are normal stresses, for a case of pure bending. Most of the time, we won't have pure bending, as there will also be a shear force acting on the beam cross-section, like the beam we saw at the start of the video. It turns out that the presence of a shear force doesn't normally significantly affect the bending stresses, and so, luckily, we can consider the flexure formula we derived earlier for pure bending to be valid for a more general case of bending. The shear force V is the resultant of shear stresses, which act vertically, parallel to the cross-section. We denote the shear stresses using the Greek letter tau. To maintain equilibrium, these vertical shear stresses have complementary horizontal shear stresses, which act between horizontal layers of the beam. One way to visualize these horizontal stresses is to consider a beam made up of several planks of wood. When a load is applied, there is a tendency for the planks to slide relative to one another. Now let's glue the planks together. When the load is applied, the planks cannot slide, and so horizontal stresses develop between them. If these shear stresses are larger than the shear strength of the glue bond, the glue will fail. These horizontal shear stresses don't exist if we apply a moment instead of a force, because that gives us a state of pure bending, and so there is no tendency for the planks to slide relative to one another. The presence of these horizontal shear stresses explains why wooden beams sometimes fail by splitting longitudinally. This failure usually occurs close to the neutral axis, for reasons which will soon be obvious. So how can we calculate the shear stresses? We can calculate the average shear stress acting on the cross-section as the shear force, V, divided by the cross-sectional area. But the shear stresses aren't distributed uniformly across the beam cross-section. The shear stress has to be zero at the free surfaces, at the top and bottom of the beam. So the average shear stress isn't very useful, since it doesn't tell us the maximum shear stress. Instead, we can use this equation to calculate the shear stresses acting on the cross-section. I won't cover the derivation of the equation here, but it's based on considering equilibrium of stresses acting on a small element within the beam. The equation assumes that the shear stress is constant across the width B of the cross-section. So tau is a function of the distance along the beam, x, and the distance above the neutral axis, y. V is the shear force acting on the cross-section, which varies with the distance along the beam. B is the width of the cross-section. It can vary with the distance y from the neutral axis, but in this case, the cross-section is rectangular, so B is constant. I is the area moment of inertia, which is a constant value calculated based on the shape of the cross-section. And Q is the first moment of area for the portion of the cross-section above the location we want to calculate the shear stress for. So it varies with the distance y above or below the neutral axis. It is equal to the product of the area above the location of interest and the distance between the centroid of that area and the neutral axis. If the location of interest is below the neutral axis, we consider the area below the axis instead of the area above it. To calculate the first moment of area at this line, which is at a distance y from the neutral axis, we multiply the area of the blue rectangle above the line by the distance from the neutral axis to the centroid. Doing this calculation gives us an equation for Q as a function of the distance y from the neutral axis for a rectangular cross-section. And so we can obtain an equation which describes how the shear stress varies with distance from the neutral axis. The y term is squared, and so the shear stress varies parabolically over the height of the cross-section, with the maximum shear stress occurring at the neutral axis. This is opposite to the bending stress, which is 0 at the neutral axis. It explains why the horizontal shear failure of a wooden beam we saw earlier occurs close to the neutral axis. By setting y to 0 in this equation, we obtain an equation for the maximum shear stress in rectangular cross-sections. It is equal to 1.5 times the average shear stress across the entire cross-section. The derivation of this equation for shear stress makes a few assumptions, so we need to be careful with how we apply it. First, it assumes that the shear stresses are constant across the width of the cross-section. For rectangular cross-sections, this is a reasonable assumption if the rectangle is thin. But for cross-sections like this one, the shear stresses can vary significantly over the width. And so in these cases, the equation can really only give us the average shear stress across the width of the cross-section. It can't tell us what the maximum shear stress will be. Another assumption this equation makes is that the shear stresses are aligned with the y-axis. Shear stresses act tangentially at a free surface. So for a circular cross-section, for example, we can't strictly use this equation to get the distribution of shear stresses across the height of the cross-section, but we can still use it to estimate the shear stresses at the neutral axis, because the shear stresses there are aligned with the y-axis. The equation for shear stress at the neutral axis in a circular cross-section is similar to the equation for a rectangular section, where we have the average shear stress V over A multiplied by a constant. The constant is 4 over 3 for a circular cross-section and 3 over 2 for a rectangular one. We can also use the shear stress equation for thin-walled sections like this I-beam, although things are a bit more complicated. Because the vertical shear stresses at the surfaces shown in red must be 0, and because the flanges are very wide, the vertical shear stress in the flanges is very small. This means that the vertical shear stress is distributed like this. The web mostly carries the shear force, and the flanges mostly carry the bending moment, as we saw earlier. You can see that the shear stresses are distributed quite evenly over the height of the web. This is because the flanges contribute significantly to the first moment of area Q when calculating the shear stresses in the web, but they don't carry much of the vertical shear force. Since the web is thin, the shear stresses are also distributed evenly across its width. Because of this, we can easily calculate the approximate shear stress in the web, like this. More detailed analysis reveals that there are shear stresses in the flanges, but they are acting mainly in the horizontal direction. The horizontal stresses on both sides of the flanges cancel each other out, so the net shear force is still just a vertical force. We can figure out the direction of the horizontal shear stresses based on the direction of the vertical shear stresses by imagining that the stresses are flowing through the cross-section. That's it for this review of bending and shear stresses in beams. If you enjoyed the video and would like to see more content like this.
Okay, guys. So I think this is what I expected you to go through before coming to this class, right? So I think now you are all aware about what is the bending stress and what is shear stress, right? How those formulas are used to analyze beams which is having a different cross sections like rectangular, circular, I section, T section, C section and all, how they behave and what will be the stresses for those sectional members. Okay, so just we gone through. So now we will go into our topic, which is direct and bending stresses. So here what I said, a member which is subjected to both direct and bending stresses will be the one where we are supposed to consider that member as a combined stressed member అనొచ్చు. Okay, why it is so called combined stressed member? Why? Because individually if the member is subjected to longitudinal load, it will be subjected to longitudinal stress or direct stress. If a beam is subjected to vertical load, it will have a bending stress. Okay, so they are all individual stresses and individual loads. If a member is subjected to load which creates member having a direct and bending stresses together, so okay, so that members are called combined stressed members under. Okay, so for that the member which we are considering it as a column here. Okay, right. First see column. What is axial load? Axial load ante entama, when load is acting along the longitudinal axis of column, right, which it produces compressive stress in column. Can you tell me few other examples which are very relative to the column, which is a member which is subjected to compression forces or compression loads? Column laga inkeven examples unnaya? Column is a member which is subjected to compression force. Inka, can you tell me any other real applications where those members are subjected to compression? Anyone?
Pedestal, sir.
Pedestal. Pedestal ante cycle pedestal.
No, sir. It is provided as a base to the column.
See, that is a bearing. And then a bearing. See, we provide bearings on the top of the column to transfer load from superstructure to substructure. That is also a compression member. Inka, we call it as a bearing.
Struts, sir, struts.
Intama?
Struts, columns, struts.
Very good. Strut is a compression member, okay, which is subjected to compression force. Inka what else? Post తెలుసా అందరికి? పోస్ట్, ఎలక్ట్రికల్ పోస్ట్. ఓకే, కాలమ్ ఎలక్ట్రికల్ పోస్ట్ కూడా ఈజ్ ఎ కంప్రెషన్ మెంబర్. ఓకే, వేర్ ఇట్ ఈస్ ఏ క్యాండిలివర్ మెంబర్, గ్రౌండ్ లో ఫిక్స్ అయి ఉంటుంది, పైన ఇట్ ఈస్ ఫ్రీ. సో బై దట్ యూ క్యాన్ సీ ఎలక్ట్రికల్ పోర్ట్స్ ఆర్ నాట్ ప్రిస్మాటిక్, దే ఆర్ టాపర్డ్. మీరు ఎప్పుడైనా ఎలక్ట్రికల్ పోస్ట్ చూడండి, కింద విడత ఎక్కువ ఉంటుంది, పైకి వెళ్ళేసరికి విడత తక్కువ ఉంటుంది. వై? Because it is a cantilever member. Cantilever member should have a resistance at support. Okay, that's why electrical post will be made with a tapered section. Okay, post is also a compression member. Inka stanchions antarama, bridges lo center lo pedda pillars kanipistayi kada, cable stayed suspension bridges. Okay, overhanging bridges lo whatever the central post will be there, they are called stanchions. They are also subjected to compression. Okay, piers, columns lage, columns we talk it in buildings, but piers antamu we consider it in bridges. Okay, inka
Rafter, sir.
Intama? Rafter. Okay, which rafter? Top rafter or bottom rafter? In a truss, which rafter will be subjected to compression, top or bottom?
Bottom.
See, rafter is a top member which is a compression member, bottom chord is a tension member. Okay, right. So adi kuda strut, but technically we call it as a rafter. Okay, inka so a jib of a crane, right? Crane ki boom untundi kada, right? So that boom is also a compression member, right? So like that there are many compression members. Okay, so when a load is acting along the longitudinal axis of column, it produces compression stresses in column. That is what an axial load. Coming to eccentrical load, a load whose line of action does not coincide with the axis of a column. It produces direct and bending stresses in the column. This is what we are going to study in this unit. Ante, axial load will create only direct stress, but this eccentrical load will create both direct and bending stress in the column. Okay, that is why we are going to consider eccentrical load in the column, okay, to calculate direct and bending stresses together. Sir, why eccentrical load will come into picture in column? Why column can't carry only an axial load? Ante, practically it is impossible to maintain axial load transferred from top story of the building to bottom story of the building. Okay, in a real application, in a real practical thing. Okay, for example, there is a 10-story building. You have constructed a ground floor, first floor, second floor, third floor, fourth floor. Do you judge, or can you able to make assure that load will be 100% axial from top to bottom? మనం assure చేయగలమా as an engineer? No, it is impossible. Why? Because as we are constructing, there will be a lot of errors. Human errors kanivandi, mechanical errors kanivandi, design errors kanivandi. There will be a lot of errors which makes column to carry eccentrical load instead of an axial load. అర్థమవుతుందమ్మా? ఎందుకంటే it is not just a single column. Column పైన ఇంకో column ఉంది, column పైన ఇంకో column ఉంది. Like that, there are around 10 columns at a single edge. So like this, whole structure ఎన్ని columns ఉంటాయి? Every column should have an axial load alone to make only a direct force in the column. Will it be possible? So practically it is impossible. That is the reason why this is the biggest challenge for the engineers to make axial load alone to transfer in the column. Anduvalla, what happens? It is not possible ani. Then what happens when it is not transferring only an axial load? Ante there is some eccentricity is taking place. Okay, ante load anedi center lo undatledu. Load anedi center nunchi away from the center untundi, right? So that load we are considering it as an eccentrical load antunam. So by considering this eccentrical load, we can able to analyze the column not only for the direct stress but also for bending stress anamata. Why? Because eccentrical load makes member to bend. Antena? Right? Mere okkari chudandi, take a rubber, try to apply load exactly at center. Rubber will try to compress. The same rubber try to apply load not at center, away from the center. Edge lo apply cheyandi load anedi top to bottom, top and bottom rubber ki edge lo apply cheyandi load, not at center. Emoutundi, rubber will bend. Why rubber is bending? Because you are not transferring load at center. It is having some eccentricity. Eccentricity makes member to bend. So when the member is bending, ante members will have a bending stress. So that's why eccentrical loads will have a bending stresses also. Okay, so this usually happens in a structural element called column. That's the reason why we are studying on column. Okay, so here you can see eccentricity, the horizontal distance between the longitudinal axis of column and the line of action of load in axial loaded column is nothing but eccentricity. Eccentricity E ante enti? The distance from the center of gravity of the section to the point where the load is acting. Okay, our distance a eccentrical distance under. Let me show that clearly in this picture. చూడండి, దీంట్లో చాలా క్లియర్ గా అర్థమవుతుంది. Effect of axial and eccentric load on column. Sorry. Effect of axial and eccentric load on column. You can see clearly the first picture where the load P is passing through the longitudinal axis of the column, right? Okay, so this is called a direct stress. What is the direct stress formula? Load to the cross-sectional area of the column. Kada? అందుకే దాన్ని P by A అన్నాం. So what about the direct stress diagram? Your stress diagram will be uniform. Why? Because load is passing through the axis. The stress will be same on either edges of the column. మొత్తం column కి both edges దగ్గర same stress ఏ ఉంటుంది. Right? Coming to the next right hand side of the picture, where you can see load is not at center. Load is with some eccentrical distance. అందుకే దీన్ని eccentrical load అంటారు. This eccentrical load will makes member to bend anamata. Okay, so that's how first one what happens. This direct load will create a direct stress. Okay, second one, this load is passing through the center of gravity with some eccentricity. Okay, then it will have a bending stress. Bending stress will be like this. So this is the direct stress, this is the bending stress, this is the combined stress anamata. Okay, so direct stress will be like this. You all know bending stress will be like this. What is the bending stress for a rectangular member? Maximum at both ends and 0 at center. Kada? And combined together, direct and bending stresses, it will be like this, which is in the form of a trapezoidal shape. Then what is the bending stress formula? Bending stress formula is equal to maximum bending moment by section modulus. Okay, so here we have to understand clearly direct stresses produces only direct loads only. Okay, I mean sorry, axial loads will produce only direct stresses only, but eccentrical loads will produce both direct and bending stresses. Okay, make a doubt రావచ్చు. Sir, when the load is eccentrical load, how direct stress will create? అన్న doubt మీకు రావచ్చు, right? Isn't it? So let me confirm. So here, whatever the load, wherever the load acts, finally it should pass through center. Avuna? Avuna kada? Right? So this load should pass through center. ikkada nu load apply chesina kuda ఏమవుతుంది? This load will pass through the center, but not same as the load which is passing through its center in the first picture. దీంట్లో ఎంతైతే లోడ్ ట్రాన్స్ఫర్ అవుతుందో సెంటర్ ద్వారా, ఇక్కడ ఆ లోడ్ అనేది మేబీ సేమ్ కాకపోవచ్చు. ఇట్ మైట్ బి లెస్, బట్ ఫైనల్లీ వాట్ ఎవర్ ద డైరెక్ట్ లోడ్ షుడ్ ఆల్వేస్ పాస్ త్రూ ద center of the column. Okay, along with direct load, due to eccentricity, the moment will create load into distance. Okay, moment create avutundi, right? Due to creation of this moment, member will have a bending stress. Okay, that's how the column will have a direct and bending stresses together. Ardhamavutunda? So that's what we are going to study in this particular unit, right? So I think you all understood the concept of direct and bending stresses now. Okay, why we are studying for the column alone? Meer adagochu, sir, why is there any possibility to have the direct and bending stresses in beams? Untaya? Is there any possibility to have both direct and bending stresses in beams? Beams will be subjected only to bending. There is no possibility of direct stress. Why? Because in beams, your direct load will become neutral. Kada? Right? Mid beam ki axial load supply cheyandi. Whatever the load acting from the left hand side will be equivalent to the load acting on the right hand side. So where the load will be neutral. That's why there is no possibility of direct stresses in the beams. Okay. Right? So that's why only beams will be subjected to bending alone. Clear? Any doubts, Amma? We will continue anyway. Last minute left, Amma. So that's why. Any doubts on this unit? Andarki basic concept ardhamainda? What is direct and bending stress? Why columns are supposed to be considered as a combined